Today's lesson is going to cover topic 10, which is gravitational fields. This is basically a continuation of topic 6, which is circular motion and gravity. Okay, so this is going to cover both topics 10.1 and 10.2, but only with respect to the gravitational portion. The electric field portion will be covered later this year, as well as what we covered last year. But it's important to know that everything that we learn about gravitational fields will basically apply to electric fields and vice versa, with a few differences which we'll cover when we talk about electricity. Today what we're going to do is we're basically going to look at Kepler in a little bit more detail. Okay, we're going to derive his third law, and then we're going to look at the potential energies associated with gravitational fields, escape velocity, and orbits, and then we're actually going to look at gravitational potential. Gravitational potential is slightly different from gravitational potential energy, similar to what we talked about last year between electric potential or voltage and electric potential energy. Okay, so first off, Kepler's third law, just as a reminder, says t squared over r cubed equals this 4 pi squared over gm. What it equals isn't as important as simply knowing that t squared over r cubed is going to be a constant. Okay, and the derivation of this comes from Newton's law of universal gravitation, the gmm over r squared. Okay, combined with the centripetal acceleration formula, or v squared over r. It's important to know the derivation because the IB frequently asks you to derive it, and the derivation is used in different aspects as well, including when we get into electricity and magnetism. So first off, the derivation of Kepler 3 starts, like I said, with the universal gravitation formula, or gmm over r squared. Okay, since when a planet's in orbit around the sun, okay, gravity is going to be your only force, and the orbit is circular, okay, or we're going to work solely with circular orbits, okay, not elliptical orbits. So at that point, my gravitational force, Fg, is also equal to my centripetal force, or mv squared over r. So I can set those two formulas, and also remember that the velocity v can be calculated by circumference over period, or the distance that it travels in one full rotation and the time it takes for that one full rotation. Okay, the two little m's cancel and I'm left with this formula, which looks a little bit ugly, but I can, rebalance that a little bit and end up with this formula. Okay, for 4 pi squared r over t squared equals gm over r squared. Okay, cross multiplying to get rid of the fraction, I get this formula, and then rewriting it in Kepler's format, I end up with this. Okay, so that's the derivation for Kepler 3. Again, it's important to remember the steps associated with this. There's really only two steps. The first one is recognizing what the force is and the formula associated with that force, in this case gmm over r squared. The second step is recognizing that that force is your centripetal force, or mv squared over r. Okay, and so yes, for Kepler 3 I have to add that extra thing that says your velocity is circumference over period, because I'm getting to the 4 pi squared part. Okay, but this derivation of applying force and setting it equal to your centripetal will be seen over and over again. Okay, so let's talk about potential energy. Okay, gravitational potential energy we're fairly familiar with, okay? It's mg delta h. Okay, but that formula is really only true close to the surface of the Earth. And the reason it's appropriate when you're close to the surface of the Earth is because the radius of the Earth is so big that even going a few kilometers, from the surface of the Earth to Mount Everest, it's not that big a difference, okay? The radius of the Earth is 6,400 kilometers. Okay, Mount Everest is, I don't know, maybe 10 kilometers. Okay, 10 kilometers in comparison to 6,400 kilometers is almost nothing. Okay, and so that delta H it's okay to do that. Okay, but when I go farther from the Earth, or when the distances get larger, I can no longer use a constant G. Instead, I'm going to have to go back to my force distance graph, okay? Because remember, the area under a force distance graph is the work done as the object is moved from point A to point B. Okay, so this is a graph of the gravitational force and the distance starting from the surface of the Earth. Okay, and so as I move that object, I'm changing the potential energy. As I move the object farther away, I'm going to be adding potential energy. If I'm moving the object closer, I'm taking potential energy away from that situation. Okay, so looking at this and remembering that the work is force times distance times the cosine of theta. Okay, that cosine of theta is going to be important. Okay, because we need to identify what force is doing the work. And when I ask a question, I'm generally asking about a specific force. Okay, is it the force, some external force moving the object from point A to point B, or was the object just allowed to move because of gravity? Okay, and so I need to look at the direction of displacement. Is it towards or away? And the direction of force, is it in the direction of the displacement? Okay, because the cosine theta will tell you if that work is positive or if that work is negative. Okay, so in this case, if I'm moving the object away from the planet, I'm increasing the gravitational potential energy. Okay, and so the amount of work that I'm doing from an external force, that's positive work. Okay, because I'm applying the force away and the displacement is away. And where is that work going? It's going into increasing the potential energy of the situation. Okay. The most common mistake people make in this is not understanding whether the work is going to be positive or negative. And we will get some practice at looking at those situations and deciding how do I differentiate those two. Okay, so potential energy. Like I said, as I move the object away from point A to point B, I'm changing the potential energy. Okay, and when the distances are great in comparison to the radius, that potential energy must be calculated because my force is no longer constant. I can no longer just say mg, that's my force. Okay, instead I'm going to have to integrate from point A to point B. Okay, integrate the force over that distance. Okay, and the area under the curve turns out to be a formula that's given as GMM over little r. This derivation is given to you on page 397 of your textbook. Okay, and it's also important to note the minus sign in front. Okay, because the minus sign indicates that this force was attractive. Remember when we had two charges, when were they attractive? When one was positive and one was negative. Okay, and so when I multiply a positive and a negative, I always end up with a negative number. Okay, two other things I want you to notice about this formula. Okay, at a distance of infinity, okay, when r is infinity, the potential energy is basically zero. Okay, because, and those of you in calculus know the limit as r approaches infinity. Well, it's zero. Okay, and that's the absolute, that's the basically what we're deciding. And that makes sense. Okay, because when the two objects are so far separated apart that I can say the distance is infinity, they don't even know each other exists. Okay, there's no energy, there's not even a measurable force really between those two objects. So they're basically separated from each other. And so therefore my potential energy is zero. Okay, the other important thing to note about this, okay, G is a positive number, 6.67 times 10 to the minus 11. Capital M is a positive number, little m is a positive number, R is a positive number. That whole quantity is positive, and the minus sign means that my gravitational potential energy must always be negative. This freaks a lot of people out. They don't understand how can your gravitational potential energy be negative. But it's just the number. Okay, because when I look at the graph of potential energy, it looks like this. Okay, and it doesn't matter as long as you realize that potential energy is always increasing as I go farther away. So the potential energy at this point here, okay, let's call it -2, is going to be greater than the potential energy at this point, okay, which is at a different radius or different distance from the center. So as I move away, yes, -2 is greater than -10. Okay, but it's kind of like that double negative that, when I'm using English, it's kind of confusing. Okay, but mathematically, there's no problem that says, well, moving from -10 to -2, I gained 8 joules of energy. Okay, and so but a lot of people get very confused with that. Okay, so in that case, let's look at what happens when I have an object in orbit. Okay, because when an object in orbit has both kinetic energy and gravitational potential energy. And so I need to always be looking at the total energy of the object. Okay, because that's what's going to be conserved in an activity. Okay, the total energy. Okay, well, the gravitational potential energy formula we just got, minus G_m_m/r. And kinetic energy must be positive because all the numbers are positive, and V, even if it was negative, gets squared anyway. Okay, so when I add these two together, my total energy must be less than or equal to 0. Because if my kinetic energy was somehow larger than my potential energy, okay, it means that the object, even when my potential energy, okay, by conservation of energy, if my potential energy goes to 0, I still have kinetic energy. Okay, and the only time potential energy goes to 0 is when the object is at infinity, and it's no longer orbiting at that point. Orbiting what? It doesn't know the object exists. It's infinitely far away. Okay, and so that's described as when you have enough energy to overcome your potential energy. That's escape velocity. You have enough kinetic energy to basically disappear. Okay, or at least disappear from that planet or sun's gravitational field. Okay, so it comes down to there are 4 rules that we're going to learn about circular orbits. In reality, it's just one rule. Okay, all the others are going to be just algebraic manipulations of that rule. So you really only need to memorize one of these, whichever one seems most comfortable for you to memorize. For me, it's the first one. Okay, and the first one basically says that your negative kinetic energy equals half the potential energy, or minus EK is equal to 1/2 EP. This is for any circular orbit. If I know the potential energy, I can calculate the kinetic energy very quickly. Okay, and when I combine this with the formula that says total energy, so E total is equal to EK plus EP, okay, I can end up with different ways of rewriting this thing. Okay, and that's an easy formula to remember, the total energy. Okay, so combining that, I can also write this and say, well, if I stick minus EK in the formula that I just wrote, okay, and multiply both sides by 2, I find that my potential energy is also equal to twice my total energy. Okay, a third way, total energy is equal to your negative kinetic energy. And the fourth way is basically saying twice the kinetic energy plus the potential energy equals 0. This is true for any circular orbit. Okay, and the derivation for that is going to be here. Okay, the first one anyway. Again, we start with the fact that your centripetal force is equal to your gravitational force. Like I said, we're going to come back to that derivation quite often, so it's important to know it. Okay, so basically mv²/r is equal to G_m_m/r². We can cancel the m's, no problem. Cancel one r on both sides, no problem, and we're left with v² is equal to Gm/r. Okay, moving from there, I know my kinetic energy formula. It's 1/2 mv², so I'm going to substitute that Gm/r into that formula. Okay, multiplying out, I get 1/2 Gm/m/r. But recognize that this formula here, the Gm/m/r, we just derived that. That's minus EP. okay, or the negative, if I multiply by a minus sign, I would get my potential energy formula. So basically, I've now said that my kinetic energy for a circular orbit is going to equal half my potential energy. All because I can set mv squared over r equals gmm over r squared. And this is the assumption that ends up saying that it only applies to circular orbits. Okay, if it's not a circular orbit, then I cannot say these are going to be equal. Okay, so that brings us to this graph. Okay, my recommendation to you is to memorize this graph. Okay, because this graph will help you in so many ways if you know how to use it. Okay, and so in this graph, kinetic energy is positive. It's on the positive side. It's got this little curve, approaches zero as I go to infinity. Your total energy is below, okay, but it's equally far as the kinetic energy. It's basically a reflection of your kinetic energy over the x-axis. Your potential energy is double that, okay? Remember, potential energy is twice the total energy. Okay, and to remember the order of it, okay, I have the mnemonic that I use called keep it up. K for kinetic energy, T for total, P for potential energy. And that's the order from the top going down. Okay, and this will help you decide a lot of things, okay, because if I have a circular orbit, okay, and I ask you which object is going faster, point A here or point B here, okay, if you can memorize this, well, the one farther away has less kinetic energy. Okay, if it has less kinetic energy, it must be going slower. Okay, and other aspects can also be derived from this graph. Okay, we'll see that as we go forward into doing some problems. And that brings me to the definition for escape velocity. Okay, escape velocity is the minimum velocity needed to escape a planet's gravitational well. Okay, not necessarily the best definition because I can't really use it. Okay, there's no formulas there. Okay, so I rewrite it in a way that'll give me formulas. Okay, basically it's saying that the minimum amount of kinetic energy, 1/2 mv squared, needed to overcome the gravitational potential energy minus gmm over r, okay, at the surface of the planet. Okay, actually at any point, but normally it's calculated at the surface of the planet. Okay, so derivation of the escape velocity. Okay, since I'm setting the two equal, okay, because at that point I have just enough kinetic energy to cancel out all the gravitational potential energy. So the 1/2 mv squared equals gmm over r. Solving for v, I end up with this formula, which is the square root of 2gm over r. This formula is in your data booklet, so you don't need to memorize it, but it does help to be able to derive this formula. How do I get there? Okay, because in certain situations, knowing the derivation is the only way to solve it rather than memorizing just the formula. Okay, so a couple of questions about escape velocity. Okay, on the Earth, okay, rocket launch sites are usually situated closer to the equator. Why? Okay, the reason is because the Earth is spinning and objects near the equator will have a greater velocity than objects near the pole. And that greater velocity basically says I already have quite a bit of kinetic energy. Okay, to get enough escape velocity, I only need to add a little bit more kinetic energy to launch the object into orbit or to launch the object into an escape velocity orbit. Okay, I don't necessarily need to always put all of my energy into launching this rocket. Okay, and so that's what locating near the equator gets me. It also means that my apparent weight at the equator is going to be less than my apparent weight at the poles. We've done that calculation before as well. Okay. Which brings me to the concept of gravitational potential. Okay, gravitational field we've talked about is the force per unit mass, or force divided by m. Gravitational potential is going to be the potential energy per unit mass. Okay, gravitational potential and potential energy are scalars. Okay, we've seen this last year when we talked about electric potential, which is electric potential energy per coulomb, or per unit charge. Okay, and so this definition for gravitational potential is kind of important. It's something you'll need to be doing and memorizing. Okay, it says that the gravitational potential at a point P in a gravitational field is the work done per unit mass in bringing a small point mass m from infinity to point P. Every single part of this is important. You must say point P. Okay, where's my... Oh, there it is. Okay, you must say point P. Okay, you must say work done per unit mass. Okay, it must be a small point mass, and it must be from infinity to that point P. Okay, the small point mass is important because if it was a large mass, I'd have to worry about measuring to the center of that mass. Okay, if you just say work done, that's energy, not potential. Work done per unit mass is important. And then the infinity to point P is basically how it's calculated. Okay, we have a similar formula for electric potential, just replacing masses with charges, and that electric field instead of gravitational field. And so that brings me to equipotential lines. We saw equipotential lines for electricity and electric fields last year. We have the same concept this year with gravity, and we will cover that again when we get to the electricity unit. Okay, close to the surface of the Earth, it's pretty much just equidistance. Okay, but when we're talking at large distances, okay, the gravitational field points towards the Earth, and my equipotential lines are these concentric circles. Okay, and because the potential difference between each pair of lines must be the same, the distance between each concentric circle increases. Okay, so a lot of times they ask you to draw the equipotential lines, and people just draw like a archery target, okay? Equal distance circles. That's not correct. Your distances must be increasing as I go away. Okay, and so that brings me to the rules for equipotential lines. We talked about these rules last year on electricity, and there's the same rules this year. Okay, the equipotential lines must always be perpendicular. Okay, so there's always got to be a 90-degree angle between the field lines, the gravitational field, which points towards the center of the object, and the equipotential lines. Always going to be perpendicular. Okay, and the direction of the field, your gravitational field or electric field, must always point towards decreasing equipotential. Okay, so if I was to label these numbers, okay, this one could be minus 10, okay, and then it would be minus 20, minus 30, and this one all the way here would be minus 40. Okay, that is decreasing potential. Okay, and I also get that from the graph that I talked to you about. Okay, the graph that I suggested that you memorize. Okay, and that brings me to work. Okay, when a mass is moved around a gravitational field, I can calculate the work done to move the mass, or the work done by the gravitational field, by looking at what equipotential lines did it start at and what line did it end at. Because the work is simply going to be the m for the moving mass times the change in my equipotential, times the change in my gravitational potential. This assumes that the mass does not change kinetic energy. It's slowly moved. Okay, sometimes again we have to worry about the plus or the minus because I need to know what force am I asking about specifically. What force is doing the moving? And what direction is the did the mass move? And that'll tell me whether it's positive or negative. The last thing I want to finish up on about is gravity inside a planet. Inside a planet, okay, only a portion of the mass is used to calculate the gravitational force. Okay, it's the portion of the mass that is at a radius less than the person's location or the object's location. All of this stuff outside the radius, okay, this like donut portion, all of this mass doesn't count, okay, because it actually cancels out. All of the mass above the person, okay, is really close, but there's not a lot of it. Okay, it's pulling that person upwards. It's actually going to be canceled out by all of the mass below him that's outside that radius. Okay, there's a whole calculus proof associated with that we're not going to get into because it'll really lose everybody, including me at this point, because I haven't done it in a while. Okay, so really I only care about this mass here, okay, the mass that's inside this radius of the object. Okay, and so when I graph it, this is what it looks like for the gravitational force. Okay, inside the surface of the planet, I have a straight line that goes up until I get to the surface of the Earth, which is then gm over r squared. Okay, actually, I guess this is gravitational field, not gravitational force. And after that, I have this, decaying curve 1 over r squared. Okay. And GEO here stands for geosynchronous orbit. We calculated that in one of the homework problems. That's about 36,000 kilometers away. It's not 0 at that point. It lists my gravitational field to be about 0.2. By the time I get to the moon, my gravitational field, Earth's gravitational field, is only 0.003. Okay, but look at the ISS, the International Space Station, or the Hubble telescope. Okay, my gravitational field there is not 0, nowhere close. Okay, it's at 8.7 at the space station and 8.2 at Hubble. Okay, so I still have a gravitational field there, a fairly large one as a matter of fact. Okay, I'm going to skip the video. You can watch that at home. Okay, but I'm going to talk about the gradient or the slope of your gravitational potential. Okay, because if I take the derivative, okay, or like I said, the slope at that point, I actually end up with the magnitude of my gravitational field. Okay, and that's a way that we can kind of look at this. Okay, like I said, we always need to be looking at our graphs and asking, does the slope of this graph mean anything? Does the area under the curve of this graph mean anything? A number of you are still working towards that skill. Okay, so I'm telling you at this point that if you have a gravitational potential graph, okay, the slope or the relative rate of change, okay, of your slope of your gravitational potential per unit distance, that's basically your gravitational field. Okay, I'm not going to go over the derivative. You guys can do that at when you on your own. Okay, but if I take a look at this, okay, this is a slope of my gravitational potential. Okay, V sub g. Okay, it's important to know that you're not doing V sub g divided by r. Okay, it must be delta V sub g divided by delta r. Okay, and so sometimes we can, the delta VG and the delta R is given in other aspects of the problem, not just in a graph. Okay, thank you very much. Oh, one last thing, okay, the gravitational potential for a system. Okay, in this case, the Earth and the Moon system. Remember, my gravitational field superimposes, or I'm just adding the two. The same with gravitational potential and gravitational potential energy. I can just take the two scalar numbers and add them. I don't even need to worry about the vector aspect of gravitational potential energy. Okay, but remember, if this is a graph of my gravitational potential, the point where I have a slope of 0, okay, or a maximum in this case, right up here, okay, my slope looks to be 0 somewhere in that spot. That's where my gravitational field must also be 0. Okay, because the derivative of this graph is my gravitational field. Okay, thank you very much.